pavements. So back in the days, a little bit of history of hot mix asphalt. Really, the whole reason of having roadways is really to get people out of the mud. The quality of the pavement of the hot mix asphalt wasn't really a big deal back then. In fact, even mixed design concepts were very simple, and people used to do or pick the same mix design. If it works in Chicago, they would use it in Phoenix, and if it works in Phoenix, they would use it in Dallas, Texas. But the reason why it used to work back then because the traffic levels were generally low across the board, so it didn't really matter to look into the weather impact of flexible pavement design or the soil underneath the pavement. None of that really mattered at that time. When I say pavement, actually, again, this is really the upper part of any roadway. So this is the man-made layer on top of the soil. So it's not just the top layer, it's actually everything that we put many layers, and they're certainly different by the time you go upper from the surface of the soil. We have what we call a sub base, and then a base, and then hot mix asphalt, which is the top layer. So really, all of those layers, we are gonna try to understand them. We're gonna design them, and as a pavement designer, you'll get to know, or you need to understand what's the required thickness. So really, if I want to draw, so this is the soil, the technical or the fancy word for the soil, and as a pavement designer, we call it subgrade. And then we have a sub base, then we have a base layer, and then we have the hot mix asphalt layer. And as a designer, again, you have to come up with what's the conceived or the developed plan for something to serve specific function. Your goal is to design how many layers needed, and also what's the thickness for required for each layer to handle the amount of traffic, to handle the weather, to handle the soil uh, strength underneath that pavement. So that's when it comes to pavement design. If you are a pavement designer, you are actually solving for the thickness required to carry certain traffic loads under material conditions and under environmental conditions. If you are a pavement analyzer, pavement analysis, actually this happens to an existing structure where now your goal is actually to solve for what are the stresses and the strains and predict the long-term performance of that pavement. For example, if I have a premature failure, you're going to go to the field, you're going to try to take a core, you're going to try to understand what are the stresses and the strains that's happening at that location. That's what we call pavement analysis. For pavement design, it's a brand new road. You're now designing a brand new road or designing maybe an overlay. So you need to come up with the required thickness for each one of these multiple layers. That's really again the major difference between the if I ask you in the exam, what's the difference between pavement design and pavement analysis? Excuse me. Yeah, well, something interesting here when it comes to pavement design, um, compared to other types of things that we build as human beings. Most civil engineering structures, they either fail immediately or they last forever. They fail immediately sometimes, again, if there's something wrong with a bridge design, like what happened in Tacoma Bridge and in Washington, the state of Washington, it fails in a matter of seconds. Or we can build road structures that they last forever. I mean, we can build structures that last almost for 50 years or more, such as water reservoirs or dams. However, pavement structures, they actually they deteriorate gradually with time. So you build a brand new road, it looks nice, looks neat, very smooth. You would love to drive on a new paved road, but then with time they gradually fail, and it takes years, sometimes again 10 years, 15, 20 years, depending on the thickness of the layers, the quality of the material. but it fails again, fails gradually with time. It's really not a sudden failure, but it's a slow progress towards failure. And that's what this picture really tells us, the difference in the concept between over designing versus the correct design versus the under design. So in this graph right here, the x-axis is actually the years, the time in years, or what we call the design life with the pavement. While the y-axis, this is the serviceability, or how good serviceability index or pavement serviceability index. It's a grade. Um, Higher the number, the better the pavement. So all the pavements can start with, or as always, as a high number with high serviceability index. And if you are really, if you happen to do the exact correct design, and if you are saying that this design, this pavement is gonna last for 20 years, so this is what we refer to the dark blue line right here. We're gonna start with high serviceability, and then the pavement is gonna digress, if you will, and is going to reach the terminal serviceability or the failure exactly at the designated design life, let's say 20 years. If you are over designing, that's actually again it's not really the best thing, because now you will be spending too much money on that roadway, which is gonna reduce your funding for other projects. But really over designing, meaning that you're gonna start at the same point, but now the pavement now is not gonna reach the terminal serviceability. It's not gonna reach failure at the design life. It's gonna take longer to do that. Again, it may sound good, and it is actually if you're just designing one road. But if you're designing multiple roads, and if you're over designing this one, that means again you're gonna spend too much money on this location, which is gonna affect the design of other places. But the worst case scenario is actually under designing a pavement structure, meaning that I'm designing a very thin structure compared to what I was supposed to do. And therefore, again, the starting point, it may look the same, but then failure now will happen way quicker, way earlier than the design life or the terminal serviceability that was supposed to reach, which is 20 years. So it can reach maybe, can can have a premature failure maybe at 15 years or 17 years or so, just as an example. So your goal again is to really to catch and reach that correct design. If the client is asking you to design it for 20 years, you would hope again to have a design that's efficient, cost efficient, but at the same time, it's not under you're not under designing it. You're reaching the exact design life by the terminal serviceability. So as I said, pavements, which is it sounds weird, but that's what it is. Pavements are designed to fail gradually with time until you reach the design life, the terminal serviceability of that roadway. A little bit of history here. I'm not gonna dive into it that much, but before 1920, which is now it's been almost a century, pavement thickness was based on experience. There was not much of really theories or equations. As I told you a couple minutes ago, if a cross section was designed in Chicago, Illinois, and it works really good there, people will implement the same thickness, the same method, the same everything in Phoenix, Arizona. Although the weather is different, the soil is different, but that's basically how things started a century ago. Um, and again, regardless, as I say, regardless of the soil type, regardless of anything else, again, things were about the same. But things starting to progress since then. The very first hot mix asphalt structure that was laid in the US was actually in 1870. That was in New York, New Jersey. And then 6 years later, they started actually paving the first sheet asphalt pavement, or what we now call it hot mix asphalt. That was in Pennsylvania Avenue in Washington, D.C. A century later, we have now about 2.7 million miles paved roadways in the US. 2.7 million miles. That's again, lots and lots of miles being paved using hot mix asphalt. Keep that number in mind, because we're going to compare it to how many miles do we have using cement pavement rigid pavements, which is the Portland cement concrete. The way we design flexible pavements nowadays, again, it evolved really from an empirical methods to limit shear failure methods, which is sometimes, again, we have a shear failure, or limiting deflection method, again, how much the pavement will deflect or rut or deform underneath the wheel path, all the way to using a simple regression method. And nowadays we are actually tackling the concept of mechanistic empirical method, which means it's 50-50 between using an empirical old method versus a mechanistic method, which is really looking now into the physical um, properties of the material, such as again the stresses and the strains and the deformation of each one of these layers. When it comes to Portland cement concrete, again the first structure also was built just before the end of the 19th century. That was the first concrete that was paved in Ohio, and then a century later, we have about 52,000 miles worth of rigid pavement. So 52,000 miles versus 2.7 million miles. So you could tell the difference. Our US highway network is heavily using still hot mix asphalt. About 95, 96% of our network is still using hot mix asphalt compared to a small amount of rigid pavements. And when it comes to designing Portland cement concrete, it hasn't really progressed that much. That we're still using the flexural stress as a major design factor. When it comes to classifying pavements, um, pavement can be classified by function. So we can have pavements that is used for airport pavements. So if you if this is something new for you, or um, if you think again, we're civil engineers, we have nothing to do with airports. That's not the case. We design airport pavements, and pavements designing airports. I mean, pavements in airports. It's a little bit different, and we have a different course to design how to design that. But also there is pavements that's used for highways and freeways, and also we design pavements that serve in parkings and local streets as well. When it comes to, we can also classify pavements using different structures. So we can have rigid pavements as Portland cement concrete, or we can have flexible pavements, which is the asphalt concrete, or we can have composite pavements, which is one layer, the bottom layer would be, let's say I have a hot mix asphalt, and then I'm gonna overlay it with a Portland cement concrete, or the other way around, where I have an existing Portland cement concrete layer, and now I'm gonna overlay it with a hot mix asphalt. Or we can have a gravel unpaved roadways. We have lots of these small roadways or um, very local streets in farm areas or in little towns that they're unpaved. It's basically gravel pavements, crushed aggregates, and then we crush it and we again make sure again it's settled, and that's basically an unpaved pavement. When it comes to other pavements in another way of making types of pavements, we have again flexible pavements, we have composite pavements, we have rigid pavements. For flexible pavements, we have conventional and we have full depth, and I'm going to explain what's the difference between these two in a little bit. And then we have the other extreme is rigid pavement. We can have jointed plain concrete, which is, as the word suggests, is basically those are the small slabs of concrete that we pour them side by side and not much reinforcement involved. Or we can have some reinforcement, which we call jointed reinforced concrete, or we can have continuously reinforced concrete, where this is fully reinforced concrete, same as if you are designing a slab. It's fully reinforced concrete, and now the joint length is almost limitless. While something in between, which is composite pavement, this is now a combination between hot mix asphalt and Portland cement concrete, where we can have again a black topping or white topping. Black topping meaning that again it's gonna be HMA on top of the Portland cement concrete, or white topping, which is the other way around. We have the Portland cement concrete, and then at the bottom, the hot mix asphalt. Let's start with the first structure, flexible pavement. This is again the most common pavement that you will be designing, and this is most of the time what we see on our roadways on a daily basis. But there are two ways of designing flexible pavement. We can have a conventional cross section, or we can have a full depth cross section. The conventional cross section, this is actually what we heavily use in the United States, where we design a cross section that's actually dependent on multiple layers. So here at the bottom, we have what we call the subgrade. So we have the natural subgrade, which is soil, and then we try to compact the top 6 inches of that soil. And then we have somewhere between 4 to 12 inches worth of sub-base course, which is gravel or lower quality crushed aggregates, and then we compact it really well. And that's what we call, again, a sub-base. And then we have a base course on top of that, and that's a good quality crushed aggregates. We call crushed aggregate base. And then on top of that, we just before we start now adding the hot mix asphalt, the true hot mix asphalt layer, we add what we call a prime coat, and I'm gonna explain those coats later on. And then we start now adding the hot mix asphalt, the true hot mix asphalt layers. The hot mix asphalt layer is basically a combination between aggregates and the binding agent, which is asphalt. Asphalt is um, a byproduct of the petroleum refinery process, the bottom product, if you will, and that's what we call asphalt, or some people refer to it as tar. I don't like that word. I like asphalt. So the asphalt, or if you are in the UK, they call it bitumen. This is where we mix about 5% by weight of asphalt plus 95% of aggregates, and this is what we use to pave the top layers of that conventional mixture. So typically, we have what we call binder course, which is a coarser aggregate gradation with somewhere between 2 to 4 inches. And then we have attack coat, and then we have another layer which we call wearing course. That wearing course is same as hot mix asphalt, but the aggregates that we use is a little bit smaller size to bring the surface to a very smooth um, standard, and that ranges also from 1 to 3 inches. And at the end of the job, you actually seal the surface with a seal coat. The other type of flexible pavement is actually the full depth. The full depth structure. This is more common in Europe, where they are willing to put a little bit more money up front because this is more expensive than the conventional structure, but they leave it actually for 30, 40 years because, as you could tell, we're not here, we're heavily dependent on the hot mix asphalt, a thick hot mix asphalt. All what they do, they have the natural subgrade, they prepare the subgrade, compact the subgrade, and then the entire structure is nothing but hot mix asphalt. Layers after layers. It's again very thick structure, and they don't use bases or sub bases. But again, it's expensive, as you may tell, but it lasts for a longer period of time. In fact, the Asphalt Institute in 1960, again, they say again that this is a cost-effective solution for heavy traffic. Um, so they are recommending it, but still, because of the budget constraints, here in the States, we still use the conventional structure rather than a full depth structure. Okay, so this is what I've gone through already. The seal coat. The seal coat is actually a thin coat of liquid asphalt and a spread of aggregates. It's similar to if you took concrete classes. It's similar to a cement mortar. So the cement mortar, which is again just sand and water and cement. In this case, now the seal coat is a liquid asphalt and sand, where we just use it to coat and seal the surface so it's water resistant, surface. While the tack coat and the prime coat are different. The prime coat, actually we added just before we start paving hot mix asphalt layers. We add it on top of, as you could see here, the tack coat is right here. I mean the prime coat. The prime coat we added just before we pave hot mix asphalt. We add it on the surface of the crushed aggregate base. Why do we do this? Again, the prime coat is typically it's a low viscosity cut back asphalt that is applied to an absorbent surface. We really like to put it in order to block all the voids in that crushed aggregate base layer. So we add it on the top, so we seal this heavily high air void structure, which is the base layer, before we start paving the hot mix asphalt layers. While the tack coat, which is actually, as you could see, it's the tack coat is we use it between the hot mix asphalt layers. It's the tack coat actually is it has a different properties. It's an asphalt emulsion diluted with water. It's used actually to bond between the surface being paved and an overlaying course. So we use it actually to link or to make those sub layers or the lifts, we like to call them hot mix asphalt lifts, to act as one layer. The thing is, most of state DOTs, they don't allow you to pave a hot mix asphalt layer more than 2 inches. So if the pavement designer come to you and say, well, I need a 6 inch overlay, or I need a 6 inch hot mix asphalt, you cannot construct this layer all at once in the field. You have to do it as three lifts. That's what like to call it lifts. So each lift is 2 inches. So what happens is, let's say you have a 10-mile job, you're gonna, for the first day, you're gonna pave the 10 miles with 2 inches. And then at the end of the paving day, you're gonna, or maybe the second day in the morning, before you lay the second lift, you're gonna now apply the tack coat and then put the second lift. And then this third day, you're gonna apply another tack coat before you add the third lift. Why? Because this tack coat is actually what's gonna make the 6 inches, which are three lifts, act as one layer. Otherwise, if you are paving one lift per day, you're gonna end up with problems with slippage between those three sub layers. So the tack coat is gonna act as really a coat or a binding to bind those three lifts to act as one structure at the end. So really, if I ask you what's the major difference between prime coat and tack coat, this is the answer. The prime coat, the goal of it is it penetrates into the underlying layer, it plugs any voids in the base course, and forms a watertight surface. While for the tack coat, it doesn't require, we don't have to have any penetration properties because it actually connect to asphalt rich sublayers anyways. And that's why here, for structural analysis purposes, the wearing and the binder course are combined into one layer, unless if it's composed of different materials. So again, that 6 inch uh, hot mix asphalt, if they if we're applying tack coat between the sub layers, and if there is no difference between the materials on the top surface layer and the bottom surface and the bottom layer, then we're gonna treat it as one layer, one structure. For the seal coat is actually, the thickness of the seal coat is way less than 1/8 of an inch. So we typically neglect the thickness when it comes to structural design. For Portland cement concrete, the structure is a little bit simpler, simply because we heavily depend on the top layer to handle most of the traffic loading, which is different than the hot mix asphalt. Hot mix asphalt, we depend on the total, all the layers. Every layer is going to handle certain amount of loading. But for the Portland cement concrete, it's a subgrade, and then we have an optional base or sub-base layer, and then we have the PCC. So the base course, again, it doesn't really contribute much to the structural capacity, but we use it, and we typically like to put it because it has other benefits. The first one is, again, we have the we it can control pumping. Pumping, really, I'm gonna define it later, but pumping, this is if you're driving on a roadway and you have either on the shoulder or the main lane, you have some of the fine materials are forming a line transverse to the traffic direction, and they get repeated every 10 or 20 feet. That's actually when the water penetrates. Let's say I have a pavement here and a PCC, and there is a crack. Water will penetrate through that crack, and now it's gonna go all the way down to the subgrade, and the water now is gonna pump all the fine materials to the surface. If I have now a vehicle right here and just getting closer to that crack. So this part of the PCC structure is gonna deflect down. So the water now is gonna get inside all the way down. It's gonna pump all the fine materials to the surface. That's what we call pumping. You're gonna see fine materials. But if you have a base layer, a good base layer, now when the water penetrates, it's going to take a longer period of time to go through the base layer until we reach the subgrade. So it typically tries to control the pumping. It also controls the frost action. If there is any frosting because of lower temperature, a base course is gonna try to limit that. And also, base course can serve as a drainage layer. Sometimes we design it to have the drainage is in the base layer where there is lots of air voids, and then we can have fringe pipes to fringe drainage layer, fringe drainage structure within the base layer. It also can control shrinkage and swelling of the subgrade if the soil is really bad and it expand and contract pretty extremely. Having a base layer, it can also control that, and also it's a good construction platform. Why it's a good construction platform? Let me draw this for you here. Let's say uh, I have here, this is the subgrade, and typically if I do not have a base layer, for example, or let's say I need to have a base layer, and I'm gonna explain for you why I need to have a base layer. Let's say this is the base layer, and now before we pour in concrete, when we bring again the machine to pour concrete, most of the time we need some reinforcement, and those reinforcements actually they are we typically build those as like a support system, and we add the reinforcement on top. So let me draw it here one more time. So I have the base layer, and then now I need to put the dowel bars or some dowels, or which is reinforcement. So the reinforcement typically it's in the mid depth of the PCC layer, like right here. In order to support those reinforcement, I have to raise it. I have to raise that reinforcement to the mid depth. How can I do this? Again, I have to have a little base here to put the reinforcement on top. So that base here is a steel base, so I can raise the rebars to be at the mid depth of the PCC layer. That base, if it's sitting on the subgrade, it's gonna be now very easy when we pump the concrete for those bases to move, and therefore the reinforcement are not gonna be exactly at the center. So, but if I have a good base layer, I can now tie these bases into the base or the sub base course layer, and now I'm gonna make sure by the time I'm pumping the concrete, those reinforcements are not gonna move at all. So that's why it's a good construction platform. Rigid pavements, again, they can be jointed plain concrete, which is those are the small joints that are closely spaced without any dowel bars, or we can have somewhere in between, which is jointed reinforced concrete. There are some steel reinforcement, and therefore we're going to end up with longer joint spacing, but we will need some dowel bars, or it can be continuously reinforced concrete, which is it's a fully reinforced concrete, steel reinforcement all over the place. There is no joints, even if it's prone to transverse crack, but those cracks are going to be hair cracks, and this pavement is going to last for a long time compared to jointed plain concrete. This here a picture of jointed plain concrete. Again, typical joint spacing. If there is not much reinforcement or reinforcement is very little, it cannot exceed 20 feet at the most. While for jointed plain concrete, again, we have minimal reinforcement. And what happens, how can we come up with these joints? Actually, what happens once we pave or once we pour in concrete, somewhere between 24 to 48 hours, the contractor has to come with the saw machine and create what I like to call a man-made crack. The joint is really a man-made crack, which is we just scratch the surface, which is just the depth of that joint is somewhere between 1/4 to 1/10 of the overall thickness of the PCC structure. And the reason why we do this, again, we're really making a man-made crack. So when concrete start to contract and expand, this is now a man-made control point where all the stress concentration will dissipate at that location. If you do not do this, especially at the right time, you're going to have random cracks all over the place, and we may end up with a premature failure. So that's why again we have those saw cut joints. For jointed reinforced concrete, now we're starting to see that the typical joint spacing is now up to 50 feet because now we're adding more reinforcement. We're having the tie bars, we have longitudinal joints, we have distributed temperature steel, we also have welded wire fabric. All of these reinforcement, they are not really structural reinforcement, but they are good reinforcement to resist any temperature changes um, induced cracks. And that's why again we end up with a longer spacing when it comes to the typical joint spacing, now up to 50 feet. The good thing again about those reinforcement, and again this is the picture that I was telling you about, so having a base course is much better than just building on top of the on top of the base course, on top of the subgrade. So if I have, this is the wheel of the truck, if it's a plain concrete, and so those two or this crack here is gonna basically make this concrete as two pieces. So the loaded piece of the PCC is gonna deflect downward, and therefore water can get through the crack and pump all the fine materials to the surface. But if I have reinforcement, even if I do have a crack, still the amount of deflection is going to be minimal, and the water is not going to have that much space to go, and therefore pumping will be minimally um, observed. For now, continuously reinforced concrete, this is now where it's fully reinforced concrete, reinforcement all over the place. There is basically, as you could see here, there's no joints at all. Still, we're gonna be seeing micro cracks, and that's totally fine. And it's different than having major cracks. This is here what the composite pavement is all about. So we can have a black topping versus white topping. A black topping, again, where we may have a sub base and we're going to have an existing Portland cement concrete, and then we decide to have a hot mix asphalt overlay on top of it, or AC overlay. AC is asphalt cement, um, which is again a different word for hot mix asphalt. Or it can be the other way around. We can have an existing hot mix asphalt structure, and we can add a Portland cement concrete overlay, and that's what we call a white top. Now we're going to shift gears to how do pavement fail. Pavement structures fail in different ways. I'm sure all of you drove today or yesterday on a pavement, and you observed lots of cracks or distresses. Pavements fail in different ways. They can fail structurally, or they can fail functionally, or they can fail in both ways. So a structural failure, as you may expect, a structural failure is actually a breakdown of one or more of the pavement components. It's actually a structural failure. That means the whole structure is failing, either one or two layers or more, while the functional failure is actually the inability to carry out the intended function without any discomfort. So really now it's all about smoothness. It's all about a comfort while you're driving. So I can have a sound structure, but the surface is too rough. Or the opposite, I can have a sound structure, I can have the surface is too smooth, which means that again it's going to be a risky drive if you are in a weather that's again cold weather and icy situation. Now the surface is too smooth. So that's really a functional failure, but I still can have a good structure. So, or we can have both. We can have again a structural failure as well as a functional failure. So how do pavement fails again? Those are the four major um, distresses that we see. There's multiple other distresses, but for the sake of this class, again, we're discussing the four major problems that we see on flexible pavements. So we can have high severity fatigue cracking. Fatigue cracking happens similar to if you're going to the gym. Assume you're going to the gym and you start having those dumbbells, and let's say it's a 20 pound, and you start and again it may feel it's easy to do it for the first 5 minutes. 10 minutes passes by, and the same dumbbells, 20 pounds, after 20 minutes you may not be able to lift it anymore. Why? You're fatigued. Your muscles now are fatigued. It's not about the 20 pounds is too much. It's about that now you've been doing it repetitively for extended amount of time. Same thing happens to pavements. Let's assume now that the pavement structure, again, this is hot mix asphalt, this is the base layer, and now with, if I have now a traffic loading on top of it, what happens now, the structure is gonna bend this way. So that bending is gonna be filled by the hot mix asphalt layer. That bending, the top of the layer is gonna feel compression because now the loading is on the top. So I'm gonna see compression at the top, while at the bottom, actually, I'm gonna see tension. So the top is gonna see compression, at the bottom is gonna experience tension. Hot mix asphalt, which is similar to Portland cement concrete, can be a good structure to resist compression, but it's not a good structure to resist tension. And that's why this type of failure, fatigue failure, it happens because of repetitive traffic loading. It starts once the pavement structure experiences tensile stresses more than the maximum tensile stress that the hot mix asphalt can handle, or what we call endurance limit. Once we exceed the endurance limit, the crack actually start and initiate at the bottom of the hot mix asphalt layer and start to propagate all the way until we see it on the surface. Typically, we see it on the surface on the wheel path. What do you mean by wheel path? So if I draw a typical 12 feet lane, I will see fatigue cracking mainly in the wheel path because this is where the most of the loading happens. The wheel path or the tires, where the tires are. So we call it fatigue cracking, or we call it sometimes alligator cracking, because the way those cracks looks like they are interconnected cracks, looks like they are similar to uh, um, uh, alligator surface or alligator back. So that's what sometimes we call alligator cracking or fatigue cracking. The other type of problems is permanent deformation, or what we like to call it rutting. Also, it happens at the wheel path, where it's actually now, again, I'm being exaggerating here, but the surface looks like this. So the surface where the wheel path, now you see it very apparent when it rains. When it rains, the water now will start join in the rutted area, and now we run into a safety issue where we call hydroplaning. Hydroplaning, basically, you're driving on a thin film of water. There is not much interaction between the vehicle tire and the surface of the pavement anymore. You're driving on a thin film of water, and that's also a big problem. The third problem is transverse crack, which is this is the crack that you typically see repetitively transverse or 90 degrees to the traffic direction. You can even feel it while you're driving. If you're driving and you feel that boom, 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 boom effect every couple seconds. This is the transverse crack. It happens because of the difference between daytime and nighttime temperature. If I have, or what we call the temperature gradient. If we have a large temperature gradient between nighttime and daytime, again, pavement now, asphalt pavement is gonna contract and expand. And once I reach certain amount of stresses exceeding the tensile strength, stresses of the pavement, it's gonna crack. And the last part, or the last type of distress is potholes. Potholes, again, as you can see, we see them on a daily basis. They are, again, it's like almost a circular pot, and it just keep collecting water. Why does this happen? It happens sometimes if um, um, we're not paving the whole lane in a uniform way. Sometimes the paver, which is the machine we use to pave roadways, the most of the heavy weight of that paver in the major mid point of the roadway, and the hang or the hand of that paver extend all the way to the shoulder or getting close to the shoulder. As you could see, this is the line of the shoulder here, and there is not much weight towards the end of that location here. So if it's not properly compacted, we're gonna end up with certain location that has high air void content. And if I have high air void content, and once it starts to rain, water will get into that location, and with repetitive loading, that location now is going to be a weak structure to be failing first. And that's why we see potholes. Most of the time, again, we see them on the edges of the surfaces. Not necessarily all the time, but if I have any place where it's weakly compacted, where I have higher voids, this is where I see potholes. This is here where I identify rutting or permanent deformation. Sometimes rutting happens because of issues of the surface layer, or it can be because of the subgrade layer. So how can I distinguish this? Is actually if I do a trench study. This is what we call a trench study. I have to go to the field, I cut through, and I want to see one of two phenomena. It's either you are going to be able to see something like this. So the entire structure is having the deformation like this, or you can see something like this. If you see the first phenomena here, the whole layers, all the layers are rutted. This is a subgrade problem. This is what we call subgrade rutting. And in this case, you have to remove the entire structure and come up with a brand new structure. If you see this case, this is now hot mix asphalt rutting. This is the problem of the top layer only, hot mix asphalt rutting. All what you need to do here, we're gonna do what we call mill and fill job. You're gonna mill the top layer and then pave it again. How can you distinguish again what kind of problem you're having? You can't tell from the surface. You really have to take a core, or even more better, to do a trench study like what you see in this picture. In this picture here, we were able to distinguish that the rutting happening only on the surface. The bottom hot mix asphalt layer or the base layer, they did not rut. So all what they needed at this case just to mill the top 2 inches and pave it again. All right, so in the general terms here, at what temperature rutting happen? Rutting happen at hot temperature. Whereas for thermal cracking, it's at cold temperatures, and fatigue cracking can actually happen at any temperature. Any temperature. How about rigid pavements? Rigid pavements, they also fail somehow similarly to hot mix asphalt, but also they fail way differently than hot mix asphalt at other types of cracks. For example, thermal cracking is the same as what I explained for hot mix asphalt. It happens 90 degrees to the traffic direction. They tend to be repetitive, and they happen because of the high difference in temperature between daytime and nighttime. Or we can see longitudinal cracking. Longitudinal cracking actually happens. It's again, it's a long. You could see a longitudinal cracking. It extend along the travel direction, and it can be caused heavily by the late sowing, which means it takes a long period of time to if the contractor is taking a long period of time to come back um, to the location and do the saw cuts, like what I told you before, the concrete is gonna start to crack by itself. It doesn't need it doesn't need much time. Somewhere between 24 to 48 hours. If the contractor doesn't come and apply the uh, the crack, I mean the joints, you're gonna start to see now the pavement is gonna start to crack by itself. So slate sawing or any poor construction technique or poor construction quality is gonna end up um, causing a longitudinal crack. Other problems that we face for rigid pavements, I think I've already told you about pumping. Again, you see these are the fine materials on the surface of the shoulder. That's the pumping. We can also see corner cracks. Again, if it's a slab like this and there is a corner here, we can see again that's corner crack. It happens because of maybe lots of air voids or repeated traffic, as well as poor construction. Faulting is actually now this is when you see there is a difference in elevation between two adjacent slabs. It happens actually as a secondary result from pumping. As I told you, if I have one layer, I mean, if I have two adjacent slabs and there is a crack, and the water now is penetrating through the surface and it's pumping all the fine materials to the surface, one of the two slabs is going to end up sinking. So we're going to end up with faulting, which is again difference in elevation between two adjacent slabs. Or we can have a joint spalling. Spalling again, if I do not have um, a good load transfer or there is not much reinforcement between two adjacent slabs, or there's not much actually enough joint spacing, we will have lots of stress concentrations here, and we're going to end up with lots of pieces or chips get spool or separate at the joint between the two adjacent slabs. That's what we call joint spalling. Or if you leave the rigid pavement with lots of problems and you leave it without any problems, you're gonna end up with this huge problem, which is called blow up or buckling, where the entire structure now is just gonna buckle to the surface, and if you end up with that problem, you need to do a major reconstruction. So in summary, there is again main differences between flexible pavements and rigid pavements. Major difference is material. For flexible pavement, again, we use hot mix asphalt with aggregates, while for rigid pavements, we use aggregates, cement, and water. The way we transfer loads for flexible pavement, we transferred it at smaller areas, and we depend on each layer to transfer the load all the way to the surface, to the subgrade. While for rigid pavement, we heavily depend on the top layer, the rigid Portland semi-concrete layer, and it typically transfers the load pretty quickly to the subgrade in a wider area. How about the cost? This is an everlasting debate. Which one is more cost efficient? The upfront cost for flexible pavement is relatively smaller compared to rigid pavement. Cement here in the country is expensive and compared to asphalt. So asphalt concrete or flexible pavement as a startup cost is much less. But with time, we typically see that rigid pavements, they need less amount of maintenance over the years compared to flexible pavements. So I would say up to like 2000s, we used to believe that rigid pavements they are more cost efficient on the long term compared to flexible pavement. But in the past, again, 20 years, we've been adding and improving the flexible pavements quite a bit to improve its longevity by adding asphalt rubber, by adding lots of different types of fibers to improve again the design life of the pavement. So now what I can tell you again, that the cost is almost the same between the two. They're getting very close to each other. So this is here again. I left you with this table, the major differences. If I can ask you this in the final exam, give me 3 or 4 differences between flexible payments and rigid payments. You should be able to tell the differences, which I just explained in a little bit. So with that, again, we finish this first part of chapter 4. Thank you.
Thank you.